Alright, let's actually start with covalent bond, because covalent bond is the main thing. Right. Now, when we talk about covalent bonding, the introduction part is the same as what you already know, right? Covalent bonding is the electrostatic force of attraction. Covalent bonding is the electrostatic force of attraction between a negatively charged shared pair of electrons and a positively charged nucleus. Now, when we talk about our covalent bonding, right? So, in covalent bonding, there are two types of bonds that we can have. We can have pi bond and we can have sigma bond, and we can have what? We can have pi bond. What is sigma bond and what is pi bond? Sigma bond is a single covalent bond. Okay, a single covalent bond is known as a sigma bond, and it is the overlap of the p orbitals. It is the overlap of the p orbitals sideways, or it is the overlap of the p orbital So a sigma bond can happen because of either overlap of the s orbital, either the s orbitals can overlap with each other, or the p orbitals can overlap, but they need to overlap vertically, or they need to actually not vertically, they need to overlap side by side. Okay, I will draw the diagram so it will make a bit more sense to you exactly what I am saying. But they will actually overlap horizontally. Now, if the same pi bond, if the same p orbital, if it overlaps linearly, if it overlaps linearly, or if it overlaps side by side, that is known as a pi bond. Let me show you how it would look like if I make a diagram for you. It can either form because of two s orbitals overlapping on each other. This is the shape of the s orbitals, right? So either the two s orbitals can overlap, they can make a sigma bond. The symbol of a sigma bond is this, sigma bond. The second way we can have is that there are two pi orbitals. If two pi orbitals overlap horizontally like this, okay? So this is a vertical overlap. This is a overlap between the s orbital. And this is the overlap between the p orbital. This is where the shared pair of electrons is going to be. So if they will, if your p orbitals overlap in a horizontal manner like this, okay, it will also form a sigma bond. A sigma bond is a single covalent bond. Now, along with a sigma bond, we can also see a double covalent bond, which is known as a pi bond, or a triple covalent bond, which is also known as a pi bond. In a double covalent bond, the p orbitals overlap linearly, like this. Like this. The p orbitals will overlap linearly. If the p orbitals overlap linearly, that is going to be known as what? That is going to be known as your pi bond. And this is a,
Yes.
yeah, Arham?
But didn't you say that if they like bond horizontally, then it's sigma, but like
Yeah,
both of them are like
yeah. So this is horizontal, right? They're in the horizontal plane, both of them.
okay. And then
And
Mr.
over here,
Pi bond, isn't that like vertical? Or is
yes, the pi
the
bond. Yeah, that's why I said linearly. Linear. They're
oh
both
okay.
linear to each
Okay,
other. Yeah,
okay.
they're both vertical to each other. That's why I said the word linearly, that they're both vertical to each other. They're doing a side by side bonding. Both of them are side by side each other, they're
Okay.
overlapping. In a sigma orbital, they will just be horizontal and they will overlap. So this is a
Because
pi.
pi bonds is always like only p orbital, right?
Yes,
It
pi
can't be
bond is
s.
pi. Yes, pi bond is always with the orbital. You cannot have it with this. Okay. So we have our sigma p orbital, and so we can have our sigma bond and we can have our pi bond. Now, there is a third type of bond that we can have, and that is known as sp hybridization. Okay, specifically we call it sp3 hybridization. What is sp3 hybridization? Basically, what happens that when p orbitals are involved in making a single covalent bond, this pi bond is when they're making the double covalent bond. Okay, so in a double covalent bond, there are two bonds. The first bond will be sigma bond, and the second bond will be pi bond. Okay, so in a
Okay.
double covalent bond, there are two bonds. First, we will have a sigma bond, and the second bond is pi bond. So think of it this way, that you know how we have p orbital in px, py, and pz. So first your px. If the px orbitals will overlap, you get a sigma bond. When the py will overlap with each other, you get a pi bond. Something like this. Something like this. So if I have, let's say, this is my px and py. So what is happening is this, that my, one second, px is also overlapping, and this py, I don't know how to draw it. One second. Right? So this px is also overlapping, and the py is also overlapping, like this. This would be a double covalent bond. So you are also seeing an overlap over here, right? This is the sigma bond. And then you're also seeing a vertical overlap. This is the pi bond. In a double covalent bond, you have both bonds. You have the sigma bond, and then you have the pi bond. Now, when we talk about our third type of bonding that we can see, that is known as sp3 hybridization. What is sp3 hybridization? Whenever a p orbital is involved in making a sigma bond, okay, it acquires an s orbital character. Okay, whenever the p orbital is involved in the whenever the p orbital is involved in the sigma bond or in the single covalent bond, okay, it modifies or it acquires a s orbital characteristic. What does that mean? That basically means this, that, for example, let's say that we are seeing a covalent bond forming between carbon and hydrogen. So carbon, if you remember, is in the p block of the periodic table, right? So a carbon is going to have p orbital. Then I have my hydrogen. Hydrogen has the s orbital. That's it, because hydrogen only has one shell. So what is going to happen, that the p orbital of the carbon atom will modify to have a s orbital characteristic, meaning that it will change its shape slightly so that it becomes a bit more closer to the s orbital. So over here you can see that the one side of the p orbital has become much more larger. One side of the p orbital has become smaller and rounder, like an s orbital. Okay, so this particular case, what has happened, that one of the lobes, use the term lobes, one of the lobes of the p orbital becomes bigger. The other one becomes smaller, it becomes more like an s orbital. Now over here, let's say that this is for
Yeah.
carbon. Yes, Arham?
This case is when the p orbital only like bonds with the s orbital or any.
No, when it makes a sigma bond, single covalent bond. Whenever p orbital is involved in a single covalent bond, then
So miss it can be a p with the p orbital as well, right?
yes, it can. I will draw that for you as well. It can be a p with a p orbital as well, no problem. As long as it's making a single covalent bond. So this is now the overlap. Okay, like this. This is how your carbon and hydrogen are going to overlap. One second. Sorry, let me not correct. Right now, this is your single covalent bond between carbon and hydrogen. So in your, for example, organic compounds, alkanes and alkenes, where we have single covalent bond between carbon and hydrogen, now you know how it actually happens,
But miss it's a
right?
p and an s orbital, right?
Yes, this is a p and a s
So
orbital.
okay, so the same thing can also happen with a p and a p
Yes,
because
the same thing can happen
but
with a
miss
p and p
how?
orbital.
Miss it has like a p orbital has just like two lobes. It doesn't have a spherical shape. So how can it form a spherical shape?
I will tell you one second. So now this is two p orbitals that are, let's say this is a bond that forms between carbon and carbon. You know how alkanes have single covalent bond between carbon and carbon. So in this case, this is a p orbital that is of two carbon atoms. These two carbon atoms can join together to give you a sp3 hybridization. These two are going to join up with each other to give you a sp3 hybridization. Now, this is a covalent bond, single covalent bond, sigma bond between carbon and carbon, like we see in our alkanes. Now, what is actually happening over here is, Aram, it is basically the modification of the p orbital. Okay? So what actually happens is this, that this is something that happens naturally. Okay, when the p orbital is involved in a sigma bond, it will acquire an s orbital characteristic. How does that actually happen? The orbital is slightly altered. The orbital is slightly altered in shape to make one of the lobe of the p orbital bigger. This happens due to mixing of atomic orbitals. Now, what actually happens that basically, uh, for example, now this can be various types of mixing, okay? But for example, what can happen, this is just an example, that in one situation, one s orbital can overlap with three p orbitals. I don't want to say overlap. This is simply mixing. Okay. So what does this mean? That the s orbital of the carbon atom might overlap with the three p orbitals of the carbon atom. Okay. So one s orbital of the carbon atom will mix. It's not overlapping. I'm not making a covalent bond. But this one carbon atom, one s orbital might merge, it might mix with the three p orbitals. So as a result, the shape of the p orbital changes because now the orbitals are all mixed up. The orbitals are all sharing the electrons. So the s orbital and two, three p orbitals will mix with each other, and they will cause the shape of the p orbital to change so that one lobe of the p orbital is bigger than the other. That's why it is known as sp3 hybridization, because one s orbital and three p orbitals. Okay, so
Okay.
this is
Miss, there
sp3.
is SP and then there is SP2 as well, right?
Yeah, you can have sp2 as well. Yes,
Okay.
if you have one s orbitals and two p orbitals, then that is sp2. So we can have sp3 hybridization, we can have sp2 hybridization. We can also have 1:1, one s orbital and one p orbital. So in that case, it is simply known as sp hybrid. Okay, so the number is simply telling you the number of s orbitals and p orbitals that are present. So
Mhm.
this
Okay.
is what you're going to end up seeing. Now, okay, one small thing that I want to say over here, that I said p orbitals slide linearly. I just want to correct because I don't think this is the correct terminology. I should not say linearly. I
What?
should say vertically actually.
Miss,
I
I
don't
was
want you
thinking,
to.
is that linear like x-axis?
Yeah, I know.
Like,
I realized that later that the word is very confusing and it might confuse you.
yeah.
It would be better if we said linearly for the sigma bond, right? But it does not make any sense. If I was thinking of it that I can use a better word, it would be better if I said that they align vertically. All right. So we can have s orbital. We can have a sigma bond, which can happen because of s orbital or p orbital. We can have a pi bond, and then in cases where a p orbital is involved in making a single covalent bond, we might see sp3 hybridization, in which case it will mix with the other atomic orbitals. So we can have one s orbital and three p orbitals, one s orbital, two p orbitals, one s orbital, one p orbital. We can see different kinds of hybrids. So based on that, the bond length, the bond strength, all of these things change based on the hybridization. Then all of these features of the bond are going to change. Now, when we talk about our covalent bond, okay, so this is the first thing that you need to know regarding your covalent bonding. Now, along with covalent bonding, there are two more things that we have to understand. We have to understand, we have to talk about, in fact, we talk about three things. One thing that we have to talk about is a new type of covalent bonding that we've never studied before, and that is dative bonding. And then we have to go over the different shapes of the molecule and intermolecular forces. So first of all, let me explain to you about a third type of covalent bond that you have, I'm sure, never studied before. Let me put a question up to you. I have. If I ask you to make a dotted cross diagram for ammonia, can you make it? NH3. Sorry, NH4. If I
Um,
asked you to annotate on the screen and draw the dotted cross diagram for ammonia,
is how many uh electrons does ammonium have in its outer shell?
it's in group 5.
Miss, it won't follow the octet rule because it will have one more electron.
What do you mean?
Um, 1 minute.
Yeah, you're right. You're right. You're right. That if
Right.
hydrogen comes over here, okay, so we get one hydrogen over here, one hydrogen over here, and one hydrogen over here. Now, if I add the electron from the third hydrogen, I'm
You got
getting,
three.
yes, so this does not make any sense. But we have the ammonium ion, right? So now
Yeah.
the question is, how is this happening? How am I getting a covalent bond over here when clearly it doesn't make any sense? That is because of something that's known as a covalent dative bond. What is a dative bond? I have my nitrogen. Let me first make for you NH3. Okay?
Okay.
1, 2, 3, and then we have a lone pair of electrons. If I bond this with hydrogen, I will see something like this. Now, what happens that let's say a hydrogen ion approaches the ammonium, right? That's how the ammonium ion normally forms. For example, I take NH3 and I react it with HCl. So I will get NH4Cl, right? Like that's the reaction that I had taught you.
Wait,
That
miss, what? You will take NH reacted with Cl?
HCl,
Okay,
right?
HCl.
So I will end up getting ammonium chloride, right?
Yes, yes.
This is how it works. So what happens that whenever a hydrogen ion approaches ammonia, what happens is this, that ammonia says hydrogen ion, because hydrogen ion is just a proton, it doesn't have any electrons. So when a hydrogen ion approaches the ammonia, what basically happens is this, that the ammonia says, oh, hydrogen ion, you know what? You seem to be pretty electron deficient. You don't have any electrons at all. You don't have any electrons. I have a lone pair of electrons. Why don't you share my lone pair of electrons with me? This is a dative bond, right? So ammonia will say, listen, why don't you go ahead and share my electrons with me? Because I happen to have a lone pair of electrons that's just lying there. It's not being used. So I can share my lone pair of electrons with you.
Miss, lone pair electrons means electrons which are not bonded.
Yes, this is
Okay.
a lone pair of electron, right? These are
Yeah.
unbonded pair of electrons. Unbonded pair of electrons is a lone pair of electrons. So what will happen that it will end up making a bond with it. It will end up making a bond with it and it will say, listen, why don't you go ahead and share my lone pair of electrons? Since you don't have any and I have a whole pair that's not bonded, why don't we go ahead and we make a bond for this? So now, this is what the final situation is going to look like. They will both make a bond with each other. When they will make a bond with each other, you will see something like this. Now you have made what? You have made a covalent dative bond. This is now known as a covalent dative bond. And if we draw it in the form, if I
Miss,
show
where is
you
the
all the
other
bonds,
electron? Where is the
one
other
second.
electron for hydrogen?
If I show you all the bonds, this is how you will show all the bonds. So the covalent bond is represented by an arrow like this. Okay. And then I can make square brackets and I can write down plus. So the arrow shows the covalent dative bond that nitrogen is actually sharing its lone pair of electron with hydrogen. That this is not a shared pair of electrons. Hydrogen is not bringing any electrons from his side. He is actually sharing the lone pair of electrons of nitrogen. So this is going to be known as a dative bond. Another term that we have for this is coordinate bond. In fact, from what I'm remembering, I think in your syllabus, coordinate bond is the term that is actually mentioned. Coordinate bond, or we can call it a dative bond. What were you saying, Arham?
So anyways, I was saying that why is the electron not shown for hydrogen, like the one extra electron?
Because hydrogen doesn't have any electron, it's a hydrogen ion, right? It's a hydrogen ion. You can't make a covalent dative bond with hydrogen atom.
But how do
It
you
has to
how
be
do you
an
know
ion.
that is an ion? How do you know
Sorry?
hydrogen how do you know hydrogen is an ion? Why can't nitrogen be an ion? Because the ion is of the whole compound.
No, okay. I am talking about before the ammonium ion forms. I'm talking about before. Before the bond forms, right? Ammonia, NH3. NH3 is a molecule,
Ye-
correct?
Yes.
Okay, so molecules are not ions. Molecules are molecules, right? We have
Yes.
molecules and we have ions. Hydrogen is the ion, okay? Since hydrogen is an ion, so it doesn't have any electrons. That's the main thing, that there will be no extra electrons because hydrogen doesn't have any electrons. It is electron deficient. Why? Because a hydrogen only has one electron, right? A hydrogen atom only has one electron. And when it turns into a hydrogen ion, it will have no electrons whatsoever because
Unless
it
it's a
would have lost
nucleus.
that. Sorry?
It's a nucleus, free radical.
Yes, exactly. So it doesn't have any electrons to share with nitrogen. Hydrogen has no electrons to share with hydrogen. Hydrogen has no electrons to share with nitrogen. That is the
Yeah.
main thing. Hydrogen is not bringing any electrons to the table. He has nothing. He is empty. Nitrogen is being kind enough to say, listen, I have two electrons by my side that I'm not using. Why don't you share them with me? So hydrogen is bringing no electrons to the table. Hydrogen doesn't have any electrons. It's a hydrogen ion. Since the bond is between molecule and ion, the ion doesn't have any electrons. So hydrogen doesn't have any electrons. So how will you have an extra electron, right? Hydrogen doesn't have any electrons. It's empty. It's an ion. So it doesn't have any electrons. And now when over here, the reason it becomes positive is because hydrogen is positive. That's why the entire molecule is going to end up becoming positive. Because now when you calculate the total number of electrons and total number of protons, so the number of protons will be greater. That's why.
Okay.
Okay, that's the reason. So over here now, for us to see a dative bond, there are two requirements. Okay, for us to see a covalent dative bond, requirement number one is that you should have one atom that has a lone pair of electrons. This is first requirement, that there needs to be at least one atom that has a lone pair of electrons. So over here we have nitrogen. Second requirement is that we need a electron deficient ion. Over here, this has to be with the electron deficient ion. I cannot make a dative bond with a atom, right? If I was trying to make a dative bond with hydrogen atom, I cannot. It has to be an ion. It has to be someone who does not have electrons. It has to be some molecule, some atom that does not have electrons. That's the requirement of it. Okay, so it has to be someone who is electron deficient, right? So I need
Yeah.
a second atom who has unfilled orbital. It needs to have an unfilled orbital, whether it's a p orbital or an s orbital, but it needs to have an unfilled orbital that can accept the lone pair. Right? So we need an electron deficient compound or an electron deficient compound that needs to be present. So only when both of these requirements are met are we going to see a covalent dative bond. So covalent dative bond does not just form randomly with it doesn't just form randomly with like your hydrogen atom or with any other atom. No, there are two specific requirements. Requirement number one, that you need a bond that is first of all it has to have a lone pair of electrons that can be donated. And secondly, you need to make sure that the second atom has to have unfilled orbitals that can actually accept the
Electron
lone pair.
deficient.
Yes, so it needs to be electron deficient. Let me
Okay.
give you another example of this. And this example might surprise you a bit. You might think, if I say aluminium chloride, you might say that Miss aluminium chloride will be an ionic compound because between metals and non-metals, we always get ionic bonding,
Will have,
right? Right?
yes.
That's now. What if I told you that aluminium chloride can also have covalent bonding? And this is something you're going to study this year. That just because you have a metal and a non-metal, that does not necessarily mean that it will be an ionic bond. Metals can
Because
also make
aluminum, I think, has 3 electrons, like a
yes,
+3 charge, and
yes.
chlorine has -1. So like it cannot be fulfilled. Like -2 and then +3
No, but if
will
you, for
have
example,
one.
I'm not saying that aluminium chloride cannot be an ionic bond. Aluminium chloride can also make an ionic bond, right?
Okay.
What if I have one aluminium and three chlorine, right? The formula of aluminium chloride is AlCl3. So, aluminium can donate electrons to three chlorine atoms, right? One to one chlorine, one to another chlorine, one to another chlorine. Because in one molecule of aluminium chloride, we have three chlorine ions. So if we have three chlorine ions, then aluminium can give one electron to each of the chlorine. So it can still make an ionic bond. It can, but it can also make a covalent bond. And this is the new thing that you will study, that just because it's a metal, that does not mean it necessarily has to be an ionic bond. Metals can also make covalent bonds. Let me show you the structure of aluminium chloride. Okay, this is aluminium and this is chlorine. One, two, three, four, five, six, seven. Now, notice something interesting. Chlorine is all happy and dandy because chlorine has 8 electrons in its outer shell, right? Chlorine is so happy. Chlorine is like, listen, I've got 8 electrons in my outer shell. I am so happy. I am wonderfully happy. But aluminium, look at aluminium. Aluminium only has 6 electrons in the outer shell. And you know that every single atom wants to have 8 electrons in the outer shell, right? That's the
Yes.
entire purpose of bonding, because they want to have a complete octet. Now, what will happen? What will happen is this, that we will see dimer formation. What is dimer formation? Let me show
Diamond?
you. Dimer, D-I-M-M-E-R.
Okay, okay.
One, two, three, four, five, six, seven. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Now, what is going to happen? That chlorine is going to say, listen, you know what? I have a lone pair of electrons. So why don't you go ahead and I will share my lone pair of electrons with you, right? Chlorine, so we have got two molecules of AlCl3. There are two molecules of AlCl3, okay? Two molecules of aluminium chloride. So aluminium, the two molecules will, what will happen, that the chlorine of one molecule will say, listen, I have a lone pair of electrons. Why don't you take my lone pair of electrons with you? And the chlorine of the first atom will say to the second aluminium, listen, I have lone pair of electrons. Why don't you share your lone pair of electrons with me? And when the final molecule is formed, right? So over here in aluminium chloride, two dative bonds are forming. In the molecule of aluminium chloride, two dative bonds are actually forming. Two dative bonds are actually forming. And when the two molecules will join together, what will happen? Let's quickly draw that. What will happen is this. This is my aluminium. One. Let's draw them diagonal to make it easy. One, two, three. Okay. So over here, I'm going to have my chlorine. And this chlorine is going to have a shared pair of electrons. Now, what will happen that another molecule of aluminium is going to come here. This other molecule of aluminium right? Now, what is going to happen over here that my 1, 2, 3, 4, 5, 6, 7. This is what the final structure is actually going to look like. Let me zoom in so you can see. Okay,
But
this is
miss,
what
it
the
won't be AlCl3 anymore, will it?
no, it will be Al2Cl6. Yes,
Yeah.
it will
So
be
miss,
Al2Cl6.
can we have AlCl3 or is it
If we
not
have
possible?
AlCl3, then it will be an ionic bond, not with covalent bonding. We can have it with ionic bonding, not with covalent
Okay.
bonding.
So like
Yeah.
Al2Cl6 is covalent.
Yes, Al2Cl6 is covalent. And over here, so now look, can we identify this is a covalent dative bond, right?
Yes.
And this is a covalent dative bond. Chlorine has shared its lone pair of electrons with aluminium. If you draw this in the form of a structural diagram, so it will look like this. Al, Cl, Cl, Cl. So this will donate its lone pair of electron to this aluminium, and this chlorine will donate its lone pair of electron to this aluminium. Right? So this is what your structure is going to finally look like, and the formula is going to be Al2Cl3. So in this case, I'm getting two covalent dative bonds. So once again, we met the two criteria that were required. Criteria number one, that you need to have a lone pair of electrons, right? You need to have an atom that has a lone pair of electrons. Number two, you need to have another atom that is electron deficient. In ammonia, it was hydrogen ion. Over here, it is aluminium atom. It is deficient in electrons because it has space for two more electrons. It has an unfilled orbital that is present. So that unfilled orbital can then accept the electrons from chlorine. So this is what your covalent dative bonds are. So now you know that we can have sigma bonds, right, which are single covalent bonds. We can have our pi bonds, which is seen in a double covalent bond. So a pi bond in a double covalent bond, the first bond is sigma, the second bond is pi bond. And then we have our sp3 hybridization, which is seen whenever a p orbital is involved in making a single covalent bond in which different orbitals will mix together. And then we can have a covalent dative bond as well. So these
That is
are the
three bonds.
sorry, Arab?
Three types of bonds, right?
Yes, so we can have three types of covalent bonds. Technically, we can also have triple covalent bond, But that is the same thing as
Double,
double
yeah,
covalent bond. Yeah.
single. I think there is single as well, right?
A triple covalent bond will have one sigma and two pi.
Okay.
Now, we need to go ahead and now, Aram, you can understand the concept of bond energy, right? Now you can understand the concept of bond energy. Now you can understand why is a single covalent bond so strong, but a double covalent bond is not, right?
Yes. It takes more energy to break the singular covalent bond because it's more
Yes,
strong.
yes. So, for example, okay, okay. So, for now you can understand why are alkenes, for example, so reactive, but alkanes are not. And the reason for that is the double bonds or a single bond. A double bond is actually easier to break than a single bond. Why is that? The reason for that is because uh, your pi bond is easier to break. A sigma bond is not easy to break at all. A sigma bond is extremely strong. A pi bond, on the other hand, is relatively easier to break. Oh, just 1 second. All right. Now, generally speaking, remember this. Shorter the bond length, right? Higher the bond energy. Okay. Now, what does this mean? This simply means that when I will break the bonds, more energy is going to be released. So, for example, if I break a single covalent bond, the energy release is not going to be that much. If I break a double covalent bond, the bond energy is going to be much greater. If I break a triple covalent bond, the bond energy is going to be even higher. What is the reason for that? The reason for that is that you have your is that because the as you increase okay, so for example, if you have a double bond, a double bond has more bond energy than a single bond. This is because the um this is because there is greater attraction between the shared pair of electrons and the nucleus. Because obviously, in a single covalent bond, you're only sharing two pair of electrons. In a double covalent bond, you're sharing four pair of electrons. In a triple covalent bond, you're sharing six pair of electrons. So as the shared pair of electrons will increase, there will be greater attraction between the shared pair of electrons and the nucleus. So bond length decreases, right? The bond length is going to decrease because they're going to get closer and closer to the nuclei. So bond length decreases. Now, since the bond length increases, the bond energy will increase. Why? Because now there is greater attraction between the shared pair of electrons in the nucleus. So I need more energy to break the bond. So remember this, that as the bond length changes, the as the bond length changes, the bond energy changes. And the bond energy is very important. Why? Because it affects the reactivity of a compound. A compound might be more reactive or less reactive depending upon how much energy it requires. So, for example, nitrogen. Nitrogen has a triple covalent bond and it's considered to be extremely unreactive. Okay, why is the reason for that? Because the amount of energy you need to break the triple covalent bond is high. That is why in your car engines, where the temperature is very high, the nitrogen can react with the oxygen and give us nitrous oxides that can lead to acid rain. That is why in our body, when we inhale air, right, air is made up of over 70% nitrogen, but our body
Yes.
does not absorb it, right? Why? Because the nitrogen is very non-reactive. But if this is something that happens in people who are deep divers, if they dive into deep waters where the pressure is very high, if you go like really deep into the sea, the water
Yes.
pressure is very high. Due to high pressure, that nitrogen can dissolve in the blood. And that is why when divers, when they normally rise, they rise very gradually and very slowly, right? They don't ever rise up abruptly. And the reason for that is because they need to give time for the nitrogen to slowly turn back into bubbles and then for the body to breathe it out, right? Because if they will
Yeah.
dive too quickly, that nitrogen will turn into bubbles, and that bubble will block the airflow into your really, really small blood vessels. So that is why. The triple covalent bond really hard to break, but it's not that we can't break them. High temperature, high pressure, you can break them very easily. But the reason why a double covalent bond and triple covalent bond are stronger is because of the fact that they have bond length is lesser. So remember
Mm.
this: shorter the bond length, higher the bond energy. Now, on the other hand, remember that a pi bond is weaker than a sigma bond. Okay, we can, when we are talking about breaking a bond, okay, the only thing that is not bond energy. Bond energy is not the only thing that matters. There are a lot of different factors that actually come into play. Okay, and when we do the topic of intermolecular forces, you will see a lot of those factors. But one of the factors is obviously bond energy. Then there is also another factor, and that is whether it is a pi bond or a sigma bond. A pi bond is easier to break simply because of the reason that simply because of what we call as our electron density. Okay, a pi bond has high electron density. So electron density is simply the way the electrons are distributed. Okay, and electron density is simply the way the electrons are distributed. So because they have a high electron density, it is easier to split them apart to make two sigma bonds. And this is what happens in alkenes, right? The double bond breaks and we can make two more single covalent bonds. For example, if I take an alkene and I react it with hydrogen, with the nickel catalyst, which was our hydrogenation reaction, we can add two hydrogen to our alkenes, right? Alkenes always give us addition reactions. So I can break the pi bond by because it has a high electron density, meaning that the way electrons are distributed or the amount of electrons, not amount of electrons, basically the density of electrons is greater. And as a result, uh, as a as a result, what happens, and the reason it has high electron density is because of the fact that you have the overlap is side by side. Okay, because the overlap is side by side, it's a vertical overlap, so that changes the density of the electrons, not the number but the way they're distributed. So when the density of the electron is higher, the bond is easier to break. How does the electron density affect the bond? That I will teach you when we do intermolecular forces. I will explain to you how the electron fluctuations can affect bonds. But Due to high electron density, they are easier to break. So that is, so I can break them and I can use those pi orbitals to make, I'm so sorry, I can use those p orbitals to make two sigma bonds, right? So p orbital pi bond is easier to break than a sigma bond. But generally speaking, despite that fact, if we just talk about bond energy, we don't talk about anything else, just bond energy. So in terms of bond energy, you need to remember that a, a single covalent bond is like requires less energy to break it. A double covalent bond requires more energy to break it. A triple covalent bond requires more energy. But if we just talk about the bonds, not about double covalent or single covalent, if we talk specifically about pi orbital and your sigma orbital, okay, so pi orbitals are easier to break. Yes, you need more energy to break a double covalent bond. But the reason for that is because it also includes the energy for the pi bond and also for the sigma bond. Okay, that's why a double covalent bond is stronger than a single covalent bond, because I am calculating the energy for the single covalent bond, but also for the energy for the pi bond. So both of them get added. But if we talk about both of them individually, so breaking the pi bond is easier, breaking the sigma bond is very, very hard. That is why alkenes are more reactive. Alkenes do not react at all unless they are under UV light.
You have single covalent bonds, right? So it's harder to break.
Yes,
Means
exactly. So they only have,
that's why polymers are also like
yes,
strong. They
exactly,
don't react.
exactly. Yes, that is why alkenes can make polymers, but alkanes cannot. This is why alkanes cannot undergo any other reaction except for the substitution reaction under UV light. Okay, everything clear so far, Aram? Any part that's not making sense? Any part that's confusing?
No, miss, I wanted to ask one question.
Yeah, go on.
In the bond energy and bond length, can I say that if there is a shorter bond, it
Yeah,
means that there is a strong attraction between the atoms.
yeah.
That's why there is more energy required to break them.
Yes, yes, you can say that. That would be
Okay,
completely correct.
okay. That's it.
All right. Okay. Okay, Anam, so we will go ahead and stop it over here for today. Now, in our next class, we will go over shapes of our molecules, right? And then, if we have time, we will also go over our intermolecular forces, or we will shape molecules in next class and then intermolecular forces later. But
Okay.
so yeah, that's what we
The
will take a
shapes
look.
of molecules like sp, sp2, sp3 like that.
No, 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 no. Like linear shape, tetrahedral, bipyramidal, like that. Okay. So when you talk about your molecules are never in a two-dimensional arrangement, right? I mean, in IGCSE, studied them as two-dimensional, but technically speaking, molecules are all three-dimensional in state. So in three-dimensional arrangement, in three dimensions, how do the electrons arrange themselves? That is different. Okay, so we can have lots of different shapes. We can have linear, we can have bipyramidal, we can have tetrahedral, we can have trigonal, we can have trigonal planar. So we can have lots of different shapes. How the electrons and how the bonds arrange themselves in three dimensions is going to be completely different. So that is why that is something we have not done before, because in IGCSE we just thought of them as two-dimensional things, right? That, oh, we just studied about them in molecules as two-dimensional, but molecules are three-dimensional. So in the way they arrange themselves in three dimensions is going to be a lot different. So that is what we're going to take a look at. They're three-dimensional ring. Okay.
Okay.
Okay, all right. Okay, enough then. We will stop it over here for today and we will continue with the topic in the next class. This is basically this covalent bonding, shapes of molecule, intermolecular forces. This is the new part that you don't know from before. Ionic bonding and metallic bonding is quite similar to what you already have studied. There's nothing new in it. So that is why I think we will do that towards the very end, because you already know that topic quite well. This is all new. This is something that you've never studied. So this is all going to be all new for you. Okay, all right. Thank you so much, Arham. I'll see you in the next class. Have a good day.